So we want to make theta as big as possible. So if we make it as big as possible, we know it's going to be less than or equal to just what? M over 5 factorial. Do you agree? Because what values, it's bounded by -1 to 1. So how do we choose the M value?
Max value.
What?
The max value.
The max value from, so it's the max, not the fourth actually, it's the max of what?
The fifth.
F5?
Less than or equal to
Less than or equal to M, right? Is everybody with me so far? Now what could we use for the M value here? Yes, we can use 1 once again. Is it going to be really common? Sure. So we let this equal to be, we let it equal 1 over 120. So do you understand how it was asking for under and over estimates? Again, I apologize for the correct. 20 and 22. It says explain the shape of the graph, and it says graph the error. So it's asking you to graph this right here using the Taylor expansion of cosine x. What does cosine x equal? Someone who hasn't spoken yet today. What does cosine x equal? Someone. Alex, what does cosine x equal? Sure. Do people agree with that?
Yes.
Nice. Is there something wrong with it, or does it work? It works? I'm not done yet. I just asked what cosine was. But we're estimating cosine what? -1. So what is cosine x minus 1 going to be? Negative x squared over plus x to the fourth over, like this, right? And this, look what this question is asking. It says, explain the shape of the graph using the Taylor series graph there. Explain the shape of the graph using the Taylor expansion of cosine x. Find a bound for the error. Find a bound for the error E naught for x less the absolute value between negative 0.1 and 0.1. So it's asking, like, around the origin, what does this look like? Now, this polynomial goes on forever, right? So how many turning points does it have? Theoretically, it has an infinite number of turning points, right? So this function has a ton of turning points, but let's look at it around x equals, if we do this around x equals 0, around x equals 0, what's cosine of 0? 1. All of these go to 0, so it's accurate, right? So it's cosine of 0 is 1, but the error is going to be right here. So it's perfect at the origin. Do you agree it's perfect at the origin? What does the right-hand function do? Well, it has a ton of curves, but of all the terms that are here, what's the one that's the most powerful? What's the one that dictates the structure more? The x squared, right? Oh, I like how you said that, the negative x squared. Very good, Chip. So that negative x squared means that around the origin, what's it going to look like? What shape is it kind of going to be? Think of a parabola facing down. So I'm going to exaggerate this. Around the origin, it looks like this. Now, what happens off in space? It goes ballistic, right? But the point is it goes down. Nice. And we're going from what to what? Negative 0.1 to what? To 0.1. So you could say it's a downward facing parabola for the general shape around that point. And then it asks, what is the, what's a bound for the error? Remember, this is, the red right there is the error function, right? That is the error function. So when you're saying a bound for the error between negative 0.1 and 0.1, you're trying to find what's the worst the error can be on there. What's the worst the error can be on there? What is the worst the error can be on there? Where's, and it's the absolute value, remember? It's E, what did they ask you for? Just E naught, right?
Be around the maxes.
What?
Negative 0.1.
At those x values, exactly, right. So when x is, so the worst, the biggest error will happen when you have x is equal to what?
Absolute value.
The absolute 0.1 or negative 0.1, right? So this is the error function right here. This is the error function. See that error function right there? What term really is the only one you're looking at if you're going to try to find a maximum of that error function? The first one. Maybe round up a little bit after that. All the other ones are really, really titanically small. So plug in 0.1 and square it and you get 0.01. Half of that is 0.00 what? 5. You can do that in your head, kids. So this one, remember how you can kind of like shave error a little bit? Like what would be a good estimate? Well, in the book, when you look this up, they call E naught. They say it has to be less than or equal to 0.001. Oh, sorry, 0.01. When in fact, you could actually make it what? If you really wanted to. You could justify it as what? 0.05, half of it. Half of it. Questions on the test are going to be way more specific than this. You are not going to have this much freedom to shave on the test. Not this much freedom. Yes, Jerry.
So
Important. Show that the Taylor series about 0 for sin x converges to sin x for every x.
what does that mean?
So remember when we did interval of convergence, everybody? I would give you a power series, right? And you guys would say, you would say, for some values of x this converges, and for some values it doesn't. Sin x, what does sin x equal? X minus, you've done this many times, plus x to the 5th over, right? They want you to prove that that's true no matter what x value you plug in. They want you to prove that no matter what x value you plug in. How do you do that? How do you do that? What is, if you looked at this, like En, you could say En, n goes to infinity. So think of it as n going to infinity, error n, okay? That's going to be less than what? M over what? N plus 1 factorial times x to the what? N plus 1. Do you agree with this so far? Are you okay? Hey, we're now back to our essential quest here. M is our goal. What's our M going to be? Y. Someone knew. Y is it 1? Yeah, no, I'm sure. Sine are bounded by 1. No matter what you plug in for x, the derivatives are always going to be less than or equal to 1. You with me so far? So we know that this is always going to be, so less than or equal to what? 1 over n plus 1 factorial this. This is where you have to remember something, that we've done something very similar, and we did it in the ratio test. X is going to be a fixed number, right? We're talking like plugging in 7, plugging in 8, plugging in 9. What about n? Not just changing, it's getting as big as you want it. So if you, effectively what's going on is you're choosing a number x. Can I always go infinitely farther than that? And what's really here, the other thing, we've proven this, but you don't have to prove it when you use it. What's the most powerful mathematical operation on the board right now? What? No. The factorial crushes this. Crushes it. Think of it this way. Oh man, let's say n was a billion, okay? So you're like, let's say x was 7. 7 to the billion power, that's big, right? How big is this?
A billion times 1 less than
Billion times 1 less than that. It's so much bigger. We've proven this using L'Hopital's rules and indeterminate form. So no matter what x is, what happens here? No matter what x is, what does this go to? As n goes to infinity, what happens to this? It goes to 0. No matter what x is, we just show that the error always goes to 0. So therefore, what have we shown? We've shown that for the Taylor series of sin x around 0, it converges to sin x. The error goes to 0 no matter what x value we choose.
So is it just as n goes to
Yes.
infinity, or is it the limit?
As n, yeah, so you're doing it. The limit as n goes to infinity of 1 over n plus 1 factorial, this is what? 0.
We just use it.
Yes, you can say that. You don't have to prove that. You can just say that. We've done it before with the ratio test, because some of those ratio test questions, the interval of convergence can be infinity, right? It means it converges everywhere. So what's the radius of convergence here? Infinity, because it converges for all x values. That's part of the reason this is so helpful. Other ones aren't as helpful, not as helpful, but like 1 over 1 minus x. What did that equal? You remember this. X plus what? Does that always work? 5. Plug in 5. Is that true for the number 5? Really? Junda?
Is it negative 1 1?
Okay, plug in the number 5 into that equation. Is it true? No. What happens to the right-hand side? 5 plus 25 plus 1, it's freaking huge, right? It does not equal negative 1/4, right? What's the interval of convergence for this? Do you remember? This works for what numbers? Exactly. So some of these expansions have a limited radius of convergence, but what about sine x? Anything goes with that one.
Oh, we always use this. It's like x always goes to 0, near 0.
Exactly. So they specifically set you up on these questions. Yeah.
I know a word for sine and cosine. There's a word for e to the x.
Ah, so we could try that. I mean, if we wanted to, that's a great question. So what about e to the x? So how did we go about doing this? Well, we want to show that the error goes to what? 0. Well, so let's try it and see what happens, right? So if we do the same work here, let's look at what we did here. We're looking at if we did e to the x instead. Let's say we did e to the x. You're still trying to show that this, okay, this is the same thing, right? N plus 1 factorial x to the n plus 1, correct? Yeah. What's the key difference we're about to run into here? M. Oh, okay, m. So we're looking for m. So you want to do f n plus 1 is less than or equal to m, right? Yeah. Correct? Yeah. Are we there so far? Yeah. You have to be very careful. Is it 1? No. What's the derivative of e to the x? E to the x. What's the next derivative? E to the x. E to the x, right? So therefore, what are we going to have to say for our m value on this? What is m going to be equal to? It's always going to be less than or equal to what? E to the what? E to the x. You with me so far? So that's bigger than what we had before, but here's the thing. What's this equal to, therefore? E to the x over factorial, right? Times x to the what? N plus 1. But here's the thing. Choosing x is functionally the same thing as e to the x as well. This is effectively a constant. This is effectively a constant, but what is this? This is a thermonuclear plasma torch, whatever you want to call it here, right? You don't have any operations that can like beat this out yet, right? So what is this always going to go to as n goes to infinity? What does this go to? 0. It goes to 0. Like you want, oh man, that's huge, right? E to a billion, what's bigger? Way bigger. A billion factorial. Because here's the thing, if this is static, you can always make this bigger.
Is there anything bigger than factorial?
Is there anything more powerful? Well, I'm using that word loosely. Like, I don't think there's enough feeling in mathematics. You know, it's like big, small, that's all relative, right? Like, we think of our sun as big. Our sun is freaking small when it comes to overall, like, the stars that are out there. Did you see the study? We're like, our sun is like average and boring. There are like hyper big giant stars that are like bigger than our solar system by like orders of magnitude. Like, I'm not kidding. There are stars that are much bigger than our solar system. Side note, did you see the study that came out where they just recalculated the number of galaxies in the known universe? Did you see this? So there's something called the Hubble bubble. This is a real thing. The Hubble Space Telescope, everybody's aware of this? Yeah. Please tell me you know what the Hubble Space Telescope is.